Welcome back to the deep dive. Today, we're grabbing a stack of source material that's pretty much gold if you're building on AWS, especially if you're maybe thinking about the Solutions Architect Associate exam.
Absolutely. We've got a set of practice questions here, and crucially, the detailed explanations that go with them. They really dive into some real-world AWS architecture problems.
Yeah, these aren't just, abstract questions. They feel like the kind of decisions and, frankly, the challenges you actually face designing systems on AWS.
Exactly. Figuring out the right service, the right setup for a specific need, and maybe even more importantly, understanding why other options that seem plausible, well, why they just don't cut it in that particular situation.
Precisely. So our mission for this deep dive, we're going to use this material as our guide. We'll unpack these scenarios, pull out the really critical bits of knowledge from the
And
explanations.
really get to the bottom of why the correct answer is correct, and just as importantly, why the wrong answers are wrong.
Yeah. It's all about getting that practical, useful knowledge straight from these pretty challenging examples. This is how we shortcut that path to being really well informed.
Okay, let's unpack this. Starting with something that definitely trips people up. Lambda functions inside of VPC and hitting those nasty throttling errors.
Yes. The scenario here is a Lambda function processing a heavy load, right? And it starts getting EC2 throttled exception errors, but only sometimes, intermittently.
Right, intermittently, which
Right.
makes it harder to diagnose. And the sources seem to really focus on the network layer for this specific error.
They do, which might seem a bit counterintuitive at first. You think Lambda, you think serverless scales automatically, right?
Yeah, that's the promise.
But the sources point out, when that Lambda function needs to talk to things inside your VPC, like an EFS file system or a database, Lambda itself has to create and manage elastic network interfaces, ENIs.
Ah, okay. To give the function an actual network presence in the VPC. Exactly. That's the mechanism the sources highlight. And if your function scales up fast because of load, it suddenly needs more of these ENIs.
So if you see that EC2 throttled exception popping up now and then,
The sources strongly suggest you're probably hitting limits related to those network resources, the ENIs themselves.
okay, limits like what specifically, according to the sources?
Well, the material flags two main culprits. Either your Lambda scaling is just plain exceeding the VPC's quota for the number of ENIs allowed, or
Or
or it's trying to create those ENIs in a subnet that's running low on available IP addresses. Both are hard network capacity limits.
And hitting those limits would show up as throttling when Lambda tries to spin up more connections. Interesting.
Yeah, hitting a network limit, but the error message mentions EC2 throttling. It's a good nugget, that connection.
So what about other things you might guess, like IAM permissions?
The sources pretty much dismiss that here. They say if it was permissions, you'd probably see an access denied type error. And crucially, it would likely happen all the time, not just sometimes.
Right. The fact it works intermittently kind of rules out a basic permission block.
Exactly. That's the logic in the sources.
Okay, what about security group outbound rules being wrong?
Similar logic. If the security group blocked the necessary outbound traffic within the VPC, the function just wouldn't work. Period.
Not intermittently.
Right. The path must be open sometimes. The sources also add that internet traffic restrictions aren't usually the root cause of this specific EC2 throttled error related to ENI creation.
And the possibility of a missing or broken NAT gateway?
Well, a NAT gateway is mostly for instances in private subnets needing to reach the public internet. This scenario seems focused on accessing resources within the VPC. Plus, the error is about throttling resource creation, not a general connection failure. The sources imply a NAT issue wouldn't typically cause this particular EC2 throttled exception.
Okay, so for you, the listener, the big takeaway here, really hammered home by these sources, is that serverless scaling inside of VPC isn't magic. It depends directly on underlying VPC resources, ENIs, IP addresses.
Yeah, hitting those network capacity limits is a real-world scaling problem. It can stop your seemingly infinitely scaling function dead in its tracks.
Yeah.
These sources show you exactly how that can manifest. Good stuff. Okay, moving on. Let's tackle high availability, specifically for a private EC2 application. The setup is a dashboard running on a spot EC2 instance.
Uh-oh. Spot instance.
Yeah.
Already thinking about potential interruptions there.
Right. And it's in a private subnet, accessed via a domain name mapping to its private IP. So the question is, how do you make that highly available? Get rapid network failover if that primary spot instance gets reclaimed.
Yeah, this is a classic pattern for fast failover inside a private network. The sources explain it really hinges on being able to shift the network identity, the IP address, basically very quickly between instances.
Okay, and the technique described in the sources involves using a secondary elastic network interface, another ENI.
That's the one. You create the secondary ENI, attach it to your primary instance first. Then, if that primary instance fails, maybe the spot instance is terminated.
You detach just the secondary ENI and quickly attach it to a standby instance that's already running and waiting.
And the magic of this, according to the sources.
The magic is that the secondary ENI keeps its private IP address and, importantly, its MC address. When you move it to the standby, the network fabric sees that familiar MC address suddenly appear associated with the standby instance.
So the network doesn't need DNS updates or route table changes.
Exactly. The sources emphasize the speed benefit. Traffic reroutes almost immediately at the network layer because the IP and MSE haven't changed from the network's perspective. They do note the scenario uses a private IP, so an elastic IP isn't strictly needed, but you can use this ENI trick to move EIPs too, if you had public access.
That is clever. Moving the network identity itself. So how does this stack up against other ideas the sources might mention as incorrect, like attaching an elastic IP to the primary ENI and trying to move that via transit gateway?
Well, first, the sources point out EIPs aren't needed for a purely private application. But more fundamentally, they say Transit Gateway connects networks. It doesn't have a feature to automatically move an EIP between instances on failure. That's not its job.
Okay. What about using AWS Network Firewall to detach and move the primary ENI?
The sources are super clear on this. You cannot detach the primary network interface, E00, from an EC2 instance. Full stop.
Right, can't do it.
And Network Firewall filters traffic. It doesn't manage instance ENIs. So that option fails on 2 counts according to the material.
And this other odd one, using AWS Transfer for FTPS to disable source-to-destination checks and reassociate the primary ENI.
Yeah, that one's way off base according to the sources. AWS Transfer is for managed FTP services, totally unrelated to EC2 ENI failover. And again, you can't detach the primary ENI. Plus, disabling source-to-destination checks is for making an instance act like a router or NAT device, not for this kind of failover.
Okay, so for you, the listener, this deep dive into ENIs really highlights a powerful specific technique. If you need super fast failover within a private network, especially for stateful apps or where DNS delays are unacceptable,
Understanding how to use secondary ENIs to move that network identity is a crucial pattern, straight from these sources.
let's switch gears to security. DDoS attacks. A startup is building a public-facing HPC app, high-performance computing. They need to mitigate potential DDoS attacks. The question asks, what methods are not suitable? What should they avoid relying on?
Right. DDoS is about being overwhelmed by bad traffic, and the sources correctly point to the standard AWS toolkit for this. CloudFront, application load balancers with auto-scaling, AWS Shield, AWS WEF, those are the real defenses.
But this question's about the red herrings. What things might sound like they'd help but actually don't, according to the sources.
Okay, the sources call it a couple specifically. First, adding multiple elastic fabric adapters, EFAs, to get more network bandwidth.
EFAs sound fancy and fast.
They are. But the sources explain EFAs are designed for inter-instance communication within an HPC cluster. Think MPI traffic. They accelerate that kind of specialized network flow, not general internet traffic absorption needed for DDoS mitigation.
So, wrong tool for the job.
Completely. Plus, the sources add a practical note. You can typically only attach one EFA per instance anyway.
Okay, so HPC network interfaces won't save you from DDoS. What's the other unsuitable method mentioned?
Using dedicated EC2 instances for maximum performance.
Why doesn't that work? Dedicated instances sound robust.
The sources clarify that dedicated instances are really a billing and compliance thing. They guarantee your instances run on hardware dedicated to your account, not shared, but they offer no inherent DDoS protection.
And just having one maximum performance instance isn't enough.
Not against a large-scale DDoS attack. That's about absorbing massive traffic volume, which requires distributed services like CloudFront or Shield, not just a beefy instance.
That's a really critical distinction for you, the listener. Performance tuning tools like EFAs or specific instance types like dedicated have their uses, but these sources make it crystal clear. Don't confuse them with actual DDoS security measures. Use the right tools. Shield, WAF, CloudFront for that job.
Use the right tool for the job, absolutely.
Okay, next up. A scenario mixing private database access and cross-account backups. We've got an EKS Fargate app, needs to talk to DynamoDB privately, no public internet allowed. And separate requirement, automated cross-account backups for DIR.
Right, two distinct needs here. One is about network routing within the VPC. The other is about backup capability.
So first, that private connection to DynamoDB from Fargate inside the VPC. How did the sources say to achieve that?
They're very specific.
Yeah.
You need to create a DynamoDB gateway endpoint, not an interface endpoint.
Gateway endpoint. Why the distinction?
The sources explain that gateway endpoints work by updating your VPC's route tables. They add routes that direct traffic destined for DynamoDB's public service endpoint range directly over the AWS private network using private IPs. It keeps the traffic entirely off the public internet. Interface endpoints use ENIs within your subnet, which isn't how DynamoDB integration works.
Got it. Gateway endpoint for DynamoDB private access. Now the second part, that automated cross-account backup for disaster recovery.
This is another key point from the sources. They state clearly that DynamoDB's built-in backup features like on-demand backups or point-in-time recovery, PITR, do not support copying those backups to a different AWS account or even a different region.
Really? So the native backups stay within the account?
Within the account in a region, according to these sources. So if you need that cross-account copy for compliance or DR,
You need something else. What do the sources recommend?
they point to AWS Backup. It's a centralized backup management service. It supports DynamoDB, and crucially, it does provide features like automated backup scheduling and the ability to copy those backups across accounts and regions.
Okay, so AWS backup is the key for the cross-account requirement. Let's quickly run through why other options mentioned don't fit based on the source material, using an interface endpoint for private access.
Wrong type for DynamoDB, as the sources said. Needs to be a gateway endpoint.
Relying only on network ACLs. NACLs.
And ACLs filter traffic, sure, but they don't create the private route. Without the gateway endpoint, traffic heading to DynamoDB's public endpoint would still try to go over the internet, even if NACLs might later block it. The gateway endpoint prevents that attempt in the first place.
Trying to use DynamoDB's own on-demand or PITR backups for cross-account copies.
Sources explicitly say, nope, doesn't support cross-account. Need AWS backup for that.
And things like AWS Network Firewall or Amazon TimeStream.
Network Firewall inspects traffic. It doesn't set up the private connectivity via endpoints. And TimeStream is a time series database completely irrelevant to DynamoDB backups.
So for you, the listener, this one drives home two critical points from these sources. First, know your VPC endpoint types. Gateway for DynamoDB is key for private access. Second, understand the limits of native service backups. For advanced needs like cross-account copies, a central service like AWS Backup is often required.
Good summary. Endpoint types and backup capabilities are fundamental.
Okay, let's think about hybrid cloud connections. A company needs a dedicated, high-bandwidth, consistent private link between their own data center and their AWS VPC, something much more reliable than just using the public internet.
Right. When you hear dedicated, private, consistent bandwidth and bypassing the internet for connecting on-prem to AWS, there's really one main service that comes to mind.
And the sources are absolutely clear on this one. It's AWS Direct Connect.
That's the answer. Direct Connect is all about establishing that physical, private network connection. It uses a standard Ethernet fiber optic cable to link your network directly to an AWS Direct Connect location.
So you literally bypass your regular internet service provider for that AWS traffic.
Exactly. That's why it provides more consistent performance and typically higher bandwidth options compared to internet-based VPNs.
It's that dedicated physical link. So why aren't the other options mentioned the primary way to create this specific kind of connection according to the sources, like Transit Gateway?
The sources explain Transit Gateway acts like a cloud router, a hub. It's great for interconnecting multiple VPCs and your on-premises network, but it still needs an underlying connection method to reach your data center. That connection could be a VPN over the internet, or it could be Direct Connect.
So Transit Gateway uses Direct Connect. It doesn't replace it for the physical link.
Precisely. It sits on top, logically. Same idea applies to the older Transit VPC pattern. The source might mention it's an architecture, not the physical connection itself.
And AWS site-to-site VPN. Why isn't that the answer for dedicated, consistent, high bandwidth?
Because, as the sources distinguish, site-to-site VPN runs over the public internet. It creates encrypted tunnels, yes, but the traffic still traverses the internet. That means performance can be variable, subject to congestion, and generally less consistent than a dedicated Direct Connect link. The scenario specifically asked for better than internet solutions.
Okay, so for you, the listener, this is really foundational hybrid cloud stuff. If your requirements scream dedicated, reliable, private, high bandwidth connection between your premises and AWS, these sources confirm AWS Direct Connect is the standard service to provide that fundamental link. Everything else often builds on top of it.
Couldn't say it better. Direct Connect is the bedrock for many hybrid setups.
Let's switch to storage. S3 storage classes, specifically S3 Standard Infrequent Access, Standard IA. The sources lay out its key characteristics.
Yep. S3 have a whole range of these classes, right? All about balancing cost against how often you need the data and how fast you need it back. Standard IA fits a specific niche.
And the sources really zero in on two main features. First, pretty obviously from the name, it's for data that's accessed
Well,
less frequently.
right, you're not hitting it all day, every day. But the second feature is the critical part, according to the sources. When you do need to access that data, it provides the same low latency and high throughput performance as standard S3.
Okay, so infrequent access, but fast retrieval when needed. That's the trade-off described in the sources. What other details do they mention about it?
They usually note the high durability, that famous 11 nines number, and strong availability, like 99.9% over a year, plus support for encryption like SSL, and it works with S3 lifecycle rules for automatically moving data around later.
Gotcha. What characteristics do the sources explicitly say are not part of standard IA?
Well, it does not automatically move data between tiers based on access patterns. The sources attribute that feature to S3 intelligent tiering.
Okay, not intelligent tiering. What else?
And they explicitly correct the idea that it might have high latency or low throughput. They emphasize its low latency, high throughput, just like S3 standard, just for less frequently accessed data.
And is it ideal for data archiving?
The sources typically position S3 Glacier and Glacier Deep Archive for true archiving long-term storage, where retrieval times might be minutes or hours, but the cost is much lower. Standard IA is for stuff you need back instantly, even if you only need it occasionally.
Right. So for you, the listener, understanding these subtle differences is pure cost optimization, isn't it? These sources remind us, match the S3 class to your actual access patterns and your retrieval speed needs. Standard IA is that middle ground, cheaper than standard if you don't touch the data often, but still instantly available, unlike Glacier.
Exactly. Saves you money without sacrificing performance when you do need it.
Okay, here's a tricky data pipeline problem involving Kinesis data streams. Scenario. You're sending IoT data from a Kinesis stream into S3. You have a process that runs, say, every 3 days to copy the data over. But you notice the files in S3 only contain data from the last day. The previous 2 days seem to be missing.
Yeah, that pattern, consistently missing older data when processing batches, strongly suggests a data retention issue within the source stream itself. How long does Kinesis actually hold on to the data?
And the sources absolutely confirm that suspicion for Kinesis data streams. They state that by default, Kinesis only keeps data records accessible for 24 hours after they're added to the stream.
There it is. That's the default retention period. So if your process only runs every 3 days.
By the time it connects to read from the stream, any data older than 24 hours has simply expired. It's gone from the stream, so it never makes it to S3.
Precisely. The sources do mention you can increase this retention period up to 7 days, I think, by enabling extended retention. But the default is just that 1 day.
Okay, so the likely cause is the default 24-hour retention expiring data before the 3-day process runs. Why aren't other explanations probable, according to the sources, like data just getting lost in the S3 bucket?
The sources usually dismiss that due to S3's incredibly high durability design, that 11 nines figure again. Spontaneous data loss in S3 is considered extremely unlikely for successfully written objects.
What about someone manually deleting the older data from S3?
Possible in theory. But the sources would argue that such consistent large-scale deletion should be trackable in CloudTrail logs, and the pattern exactly 2 days missing every time points more towards a systemic issue like retention rather than repeated manual actions.
And insufficient permissions for Kinesis to write to S3.
The sources counter that if permissions were the problem, you likely wouldn't get any data into S3, or the errors would be consistent. The fact that the most recent day's data is successfully landing in S3 suggests the basic permissions and connection are working.
Right. So for you, the listener, this is a critical lesson from these sources about streaming services. Know the default retention periods. If your downstream processing interval is longer than the default retention, you will lose data unless you explicitly configure extended retention. Don't get caught out by the defaults.
Yeah, defaults can bite you if you don't check them.
Okay, let's tackle a scenario that probably keeps some people up at night. Accidental deletion. A junior engineer accidentally deletes important user data from an S3 bucket. Yikes. How can you configure an S3 bucket to provide strong protection against both accidental deletion and accidental overwriting?
Yeah, protecting critical data from human error is paramount. S3 offers a couple of key features that work together to create a really robust safety net, according to the sources.
And the sources highlight this combination of two specific features.
That's right. First, absolutely fundamental. Enable versioning on the bucket. The sources explain that versioning tells S3 to keep previous versions of an object every time it's overwritten or deleted.
So if someone deletes an object, it's not truly gone, it just creates a delete marker, but the old versions are still there.
Exactly. And if someone overwrites an object, the old content becomes a previous version. This means you can always recover from unintended changes or deletions by retrieving an older version.
Okay, so versioning provides the recovery mechanism. What's the second layer the sources mentioned, specifically to make permanent deletion harder?
That's enabling multi-factor authentication delete, or MFA delete. The sources state that with MFA delete turned on, certain highly sensitive operations, like changing the versioning state itself or permanently deleting a specific object version, require not just the user's regular credentials, but also a valid code from their configured MFA device.
Ah, so it adds that extra physical authentication step for the really destructive actions.
Precisely. It makes it significantly harder to accidentally, or even maliciously without also compromising the MFA device, perform an irreversible deletion.
So the combination is versioning for recoverability and MFA delete for an extra guardrail against permanent loss. Why aren't other methods sufficient, according to the sources, like only allowing access via pre-signed URLs?
The sources clarify that pre-signed URLs are about granting temporary, specific access to an object. They don't inherently prevent someone who already has delete permissions on the bucket, via IAM policy perhaps, from deleting the object using standard API calls or the console.
What about using an IAM bucket policy to just flat out disallow the S3 delete object action?
The sources point out that this would block all deletions, even legitimate ones needed for cleanup or application logic. The goal usually isn't to prevent all deletes, but to protect against accidental ones while still allowing intentional actions, perhaps protected by MFA delete. A blanket deny is often too blunt an instrument.
And enabling S3 intelligent tiering, does that help?
Nope. The sources are clear that intelligent tiering is purely about cost optimization by moving data between access tiers based on usage. It offers no protection against deletion or overwriting.
Okay, so for you, the listener, these sources are really underlining a core S3 security best practice. For any bucket containing important data, enabling versioning and MFA delete is the recommended configuration to protect against human error. It's a relatively simple setup that provides significant peace of mind.
Absolutely essential for critical data buckets.
Let's talk database stealing. Aurora read replicas. The scenario is they're getting swamped during peak read traffic times, causing performance bottlenecks. You need a cost-effective solution to handle these unpredictable surges without just throwing money at oversized instances all the time.
Yeah, this is a common challenge. Workloads fluctuate. Static provisioning means you're either paying too much when it's quiet or struggling when it's busy. The sources point toward automation for cost effectiveness here.
And they highlight a specific Aurora feature designed precisely for scaling read replicas automatically.
Yes, that feature is Aurora Auto Scaling. The sources describe how you configure this to automatically adjust the number of read replica instances in your Aurora cluster. It does this based on metrics you define, like the average CPU utilization across the replicas, or perhaps the number of database connections.
So it watches the load, and if CPU gets high, it adds another replica, and if CPU drops, it removes one.
Exactly that. The sources emphasize this dynamic adjustment. You get more read capacity when demand spikes, maintaining performance. But critically, it scales down when the load subsides during off-peak hours.
Which directly impacts the cost, right?
Right, that's the cost-effective part. You're only paying for those extra replica instances when the workload actually requires them, rather than paying for peak capacity 24/7.
Makes perfect sense for variable loads. Why aren't other scaling approaches seen as the most cost-effective for this specific problem, according to the sources? Like just making the primary Aurora DB cluster instance bigger.
The sources argue that just statically upsizing the instance class isn't cost-effective for intermittent peaks. You'd pay that higher instance cost constantly, even when the extra power isn't needed.
What about using Aurora Global Database for read scaling?
Aurora Global Database is powerful, but the sources position it mainly for cross-region disaster recovery, or serving reads to globally distributed users. It adds complexity and cost, especially with interregion data transfer fees. For a read bottleneck within a single region, it's presented as overkill and likely not the most cost-effective fix.
Similar reasoning for just setting up a read replica in a different region then.
Pretty much. The sources would point to the added interregion data replication costs and complexity. Again, it's more for cross-region use cases, not necessarily the cheapest way to solve a local read scaling issue.
Okay, so for you, the listener, if you're using Aurora and facing unpredictable read traffic peaks, these sources strongly suggest looking at Aurora auto-scaling for your read replicas. It's presented as the recommended cost-effective way to match capacity to demand dynamically, ensuring performance without overspending.
It really is the sweet spot for variable read workloads on Aurora.
Let's dive back into some complex networking, this time involving IPv6 scenario. You have an EC2 instance, it's in a private subnet, it needs to initiate connections out to the internet using IPv6, but crucial requirement, you must prevent connections initiated from the internet coming into that instance over IPv6. And as a bonus challenge, all that outbound traffic needs inspection and filtering.
Okay, yeah. IPv6 has different mechanics than IPv4, especially around public versus private and internet access. And adding stateful inspection layers, you need the right combination of VPC components.
So first, that requirement for outbound-only IPv6 internet access from a private subnet. What specific VPC gateway do the sources say handles this?
For IPv6 outbound only, the sources specify using an egress-only internet gateway.
Egress only. How is that different from a regular internet gateway?
A standard internet gateway allows both inbound-initiated and outbound-initiated IPv6 connections. The egress-only IGW, as the name implies, is specifically designed just for the egress case. It lets instances in your private subnets reach out over IPv6, but it fundamentally blocks any connection attempts initiated from the internet trying to come back in over IPv6.
Ah, perfect for the requirement. Okay, egress-only IGW solves the outbound-only part. Now, the traffic inspection and filtering requirement.
For that piece, the sources recommend deploying AWS Network Firewall. They describe it as a managed, stateful firewall service. It gives you features like intrusion prevention, IPS, web filtering, and general firewall rules, and it integrates directly into your VPC traffic flow for inspection.
So the solution presented by the sources is that combination. Egress-only internet gateway attached to the VPC for the IPv6 outbound control, and AWS Network Firewall deployed to inspect the traffic passing through.
That's the pairing they recommend for meeting both requirements.
Why do the sources say other options miss the mark? What about, say, AWS Private Link or Amazon Guard Duty?
The sources explain Private Link is for private connectivity to specific AWS services or partner endpoints, not general internet access control or filtering. And Guard Duty is a threat detection service that analyzes logs and events, but it doesn't actively inspect or filter live network traffic like Network Firewall does.
What if you just put the instance in a public subnet with a regular internet gateway?
That fails the core requirement. According to the sources, a regular IGW allows inbound-initiated IPv6 connections from the internet, which the scenario explicitly forbids. You need the egress-only IGW to block that.
And using a NAT gateway along with AWS Firewall Manager.
Sources clarify NAT gateway is primarily for IPv4. While it has NetT64 for IPv6 to IPv4, it doesn't provide the IPv6 egress-only control needed here. That's the egress-only IGW's job. And AWS Firewall Manager is for centrally managing firewall policies across accounts. It's not the firewall service itself doing the inspection, which is Network Firewall.
Got it. So for you, the listener, this is a great illustration from the sources. Specific network requirements, especially with IPv6 and security layers like inspection, demand knowing the precise role of each VPC component. Egress-only IGW for outbound-only IPv6, Network Firewall for stateful inspection, understanding these specific tools is key.
It really highlights the granularity available in AWS networking.
Let's look at database security again. Authentication this time. You have an RDS MySQL database, and you need applications running on EC2 instances to authenticate to it using temporary tokens derived from the EC2 instance's own IAM profile credentials. No static passwords allowed.
Yes, getting rid of hard-coded or configuration file database passwords is a huge security win. AWS provides an integrated way to do this using IAM.
And the specific feature the sources point to is enabling IAM-DB authentication on the RDS instance itself.
That's the one. The sources explain IAM-DB authentication is a feature available for MySQL and PostgreSQL engines in RDS. When enabled, it allows clients like an application on an EC2 instance to connect using temporary authentication tokens instead of passwords.
And how are these tokens generated?
They're generated using standard AWS Signature version 4 signing processes. The application uses the AWS SDK, leveraging the credentials associated with the EC2 instance's assigned IAM role, its instance profile, to request a short-lived token from RDS. The sources mention these tokens are typically valid for only 15 minutes.
So the EC2 instance effectively uses its own IAM identity to get a temporary password for the database connection.
That's a great way to put it. The sources emphasize this eliminates the need to manage or distribute static database credentials. Authentication is handled via IAM policies, controlling who can request these tokens. They also note this method requires the database connection to be encrypted using SSL.
IMDb authentication, that's the key feature name. Why do the sources say other options aren't the right solution here, like just configuring SSL?
Sources clarify SSL encrypts the connection data, encryption in transit, but it doesn't handle the authentication part, proving who the client is. You still need a password or a token for that. SSL is necessary but not sufficient.
What about saying the solution is using a combination of IAM and STS?
While technically true that IAM and the Security Token Service, SPS, are involved under the hood in generating those temporary tokens, the sources frame the actionable solution as enabling the specific feature called IAM-DB authentication on the RDS instance and configuring the associated IAM policies. That's the direct mechanism you configure.
And just creating an IAM role and assigning it to the EC2 instances, isn't that enough?
The sources point out that's a necessary prerequisite. The EC2 instance needs that role to have the identity and permissions to request the token. But simply assigning the role doesn't automatically switch the database to accept token-based authentication. You still need to enable IAM-DB authentication on the RDS side and grant the necessary permissions via IAM policy.
Right, it's a multi-part setup. So for you, the listener, these sources are highlighting a major security best practice. If your EC2 instances connect to RDS MySQL or PostgreSQL, strongly consider using IAM-DB authentication. It replaces static passwords with temporary IAM-managed tokens, significantly improving your security posture.
It really should be the default choice for new applications where possible.
Okay, shifting focus to the operational side. Cost management. A company needs a way to programmatically retrieve potentially very large data sets of their detailed AWS usage and cost information. They need this data efficiently, maybe for feeding into internal reporting or analysis tools.
Ah, yes. Getting programmatic access to the billing fire hose. When you need detailed data, potentially lots of it, and you need to automate the retrieval, there's a primary API for that.
And the sources are quite direct. Use the AWS Cost Explorer API.
That's the recommended tool according to the sources. The Cost Explorer API lets you query your cost and usage data programmatically. You can ask for aggregated data or get quite granular filter by service, by tag, by operation, look at usage types.
And what about handling those potentially very large data sets efficiently?
The sources specifically call out the need to use pagination when interacting with the Cost Explorer API. Because the results can be huge, the API breaks them down into pages. Your code needs to request one page, process it, then request the next page using a token provided in the response, and so on until all data is retrieved.
So Cost Explorer API plus pagination is the efficient programmatic method described by the sources. Why are other options considered less suitable for this requirement, like just downloading the CSV reports?
The sources emphasize the programmatic need. Downloading CSVs from the console is a manual process. It doesn't scale and isn't efficient for automated regular retrieval of large datasets for system integration.
What about configuring AWS budgets to send notifications via SNS?
Sources explain AWS budgets is for setting spending thresholds and getting alerts when you approach or exceed them. It notifies you about your budget status, but it doesn't provide the raw, detailed cost and usage data itself for analysis.
And generating AWS budgets reports and delivering them via SQS.
Similar issue. Budgets reports focus on your spending against your budget goals and forecasts. They're useful reports, but according to the sources, they don't provide the comprehensive, queryable, detailed usage and cost data that the Cost Explorer API offers for deep dives or system integration.
Okay. So for you, the listener, if your organization needs to get serious about cost analysis, integrate AWS cost data into your own tools, or automate financial reporting, these sources point squarely at the AWS Cost Explorer API as the fundamental tool. And don't forget that tip about pagination for handling the volume.
Essential for any kind of automated cost management workflow.
All right, let's swing back to EC2 auto-scaling one more time. You've got an auto-scaling group, maybe for a web application, with variable, unpredictable traffic. The primary goal is to avoid over-provisioning to save money, but you absolutely cannot let performance suffer during those unpredictable traffic spikes.
Yes, the classic dynamic scaling challenge. Efficiency versus performance under uncertainty. You need the scaling to be smart and reactive.
And the sources strongly recommend one particular type of dynamic scaling policy as the best fit for this common scenario.
That policy is target tracking scaling. The sources describe this as the go-to for most situations like this. You pick a key metric like the average CPU utilization across the group, or maybe the request count per target from the load balancer if it's a web app.
And you set a target value for that metric.
Exactly. You tell autoscaling, I want the average CPU to stay around, say, 50%. Then, the target tracking policy automatically adds or removes instances as needed to keep that metric as close to your target as possible.
So it's constantly adjusting capacity to meet the desired performance level, rather than just reacting to high-low alarms.
That's the key difference highlighted by the sources. It proactively tries to maintain the target metric. This means it scales up when load increases to bring utilization back down towards the target, and scales down when load decreases to bring utilization back up towards the target, thereby optimizing costs by avoiding unnecessary idle instances while maintaining the desired performance level.
That sounds pretty ideal for unpredictable loads. Why are the other scaling policy types less suitable here, according to the sources? Simple scaling.
Sources explain simple scaling policies have that cooldown period after each scaling action. They have to wait before they can trigger another scaling event. This lag can cause problems with rapidly fluctuating traffic, either scaling up too slowly, hurting performance, or scaling down too slowly, wasting money.
What about scheduled scaling?
Scheduled scaling is great, the sources say, but only for predictable load patterns. Like, traffic always triples at 9 a.m. on weekdays. It's not designed to react to unpredictable spikes throughout the day.
And suspend resume scaling processes.
That's just for manually turning auto-scaling on or off temporarily. The sources clarify. It's not a dynamic optimization policy itself.
Okay, so for you, the listener, these sources make a compelling case. For most applications with variable or unpredictable load running in an auto-scaling group, target tracking scaling is the recommended policy. It offers the best balance, automatically adjusting capacity to maintain performance while minimizing costs based on real-time metrics.
It's generally the smartest and simplest dynamic policy to configure these days.
All right, final scenario for this deep dive. Serving private S3 content through CloudFront. You have, say, training videos stored in an S3 bucket. You want employees to access them via CloudFront for performance and caching, but it's absolutely essential that no one can just grab the direct S3 URL and bypass CloudFront. The S3 bucket itself must remain private.
Yeah, this is a fundamental security setup for CloudFront origins. You need CloudFront to be able to fetch the content, but you want to lock the S3 bucket down from direct public access.
And the sources point to a specific CloudFront feature as the modern recommended way to establish that secure connection.
Yes, they recommend using Origin Access Control, or OAC. You create an OAC configuration within CloudFront. Then you go to your S3 bucket policy and add a statement that specifically grants S3 get object permission only to the CloudFront service principal, but conditioned on the request coming via that specific OAC.
So the OAC acts as CloudFront's verified identity for accessing that bucket, and the bucket policy explicitly allows only that identity.
That's the mechanism. The sources emphasize OAC is the successor to the older Origin Access Identity, OAI, and is recommended for all new setups. By locking down the bucket policy to only allow access via the OAC, you effectively block all direct access attempts to the S3 objects. All requests must come through your CloudFront distribution.
Got it. OAC is the key. What about other approaches the sources might list as incorrect, like creating an IAM user for CloudFront?
The sources state you can't do that. You don't assign a standard IAM user credential to a CloudFront distribution for origin access. OAC is the purpose-built mechanism.
What about trying to create an S3 bucket policy that lists the CloudFront distribution ID as the principal?
Sources clarify that's not the right syntax or approach. You use the CloudFront service principal, cloudfront.amazonos.com, in the policy, and then use a condition key, typically referencing the OAC ID, or sometimes the distribution ARN for OAI, to restrict which CloudFront resource can access it. You don't put the distribution ID directly in the principal element for this purpose.
And using AWS WAF, Web Application Firewall, to block public S3 access.
WAF operates at the edge, on the CloudFront distribution itself, or ALBs, etc., to filter incoming web requests based on rules you define, like blocking SQL injection or specific IPs. The sources explain it doesn't manage the origin access control between CloudFront and S3. Protecting the origin from direct access is the job of OAC and the bucket policy, not WAF.
Okay. So for you, the listener, if you're using CloudFront to serve content from a private S3 bucket, these sources make it absolutely clear. Origin Access Control, OAC, combined with a correctly configured S3 bucket policy, is the essential security configuration. It ensures your users must go through CloudFront, leveraging its features and security, and cannot bypass it to hit your origin directly.
It's a non-negotiable setup for private S3 origins with CloudFront.
Wow, okay, that was quite the journey through those scenarios. We hit Lambda scaling limits, ENI failover, DDoS myths, private DynamoDB access, direct connect, S3 classes and protection, Kinesis retention, Aurora scaling, IPv6 egress, RDS IAM off, Cost Explorer, auto scaling policies, and CloudFront origin security.
Yeah, it was a dense pack. And I think the common thread through all these sources, all these examples, is really about the importance of understanding the specifics, how services actually behave, how they interact, what the defaults are, and what specific configurations solve specific problems.
Absolutely. These practice scenarios, as described in the sources, aren't just abstract. They really highlight those common tripwires, the things that can go wrong if you don't know the details, like Lambda hitting ENI limits or Kinesis data just vanishing because of the default retention.
Exactly. It's about moving beyond just knowing the service names and understanding the mechanisms, gateway endpoints versus interface endpoints, OAC versus IAM users, target tracking versus simple scaling. That detailed knowledge is what leads to robust, secure, and cost-effective architectures in the real world.
Totally agree. And digging into these specific examples, like we just did, pulling out those nuggets from the explanations, that feels like the fastest way to get that practical, applicable knowledge, to get truly well-informed quickly.
It shortcuts a lot of trial and error for sure.
So building on all that, here's a final thought for you, the listener, to take away from this deep dive. Given how much these sources emphasize specific configurations and default behaviors, what's one specific AWS service setting or default configuration in your own projects, maybe one you haven't looked at in a while, that you should probably double check right now to avoid an unexpected issue like the ones we've just discussed? Thank you for joining us for this deep dive. We hope these insights distilled from these sources help you build even better and more confidently on AWS.